Hello everybody, welcome to our first video on mechanics. This is a first year course that most university level students are taking. And the reason I have this title here, Mechanics for Students, with dummies crossed out, is because students are dummies and professors fail to realize this every year. They have these pre-assembled lecture slides that simply go through all of their basic notes that are straight from the textbook, and they don't break it down in a way that students can understand. And that's kind of my goal for this video series, is I want to teach this as simply as possible, but also cover all of the important concepts while glazing over anything that's kind of not really important. So in order to understand these concepts, I have a quick breakdown and then we're going to go into problems. This first video is on units and dimensions, which is a super simple concept. And if you want to skip this, just click on the timestamp below so you can get straight to problems if you learn better that way. But if you stick around for about 4 minutes or so, I'll go through the basics of this concept so that we can hop into problems if you're brand new to the concept and mechanics in general. So what is mechanics? Mechanics in physics is just concerned with how forces act on bodies, pretty much. So these bodies can be in motion and accelerating, which means they're dynamic, or they can be at a constant velocity or not in motion, meaning that they're static. And there's basic units of analysis for all of these different bodies, and that would be length, time, mass, and force. And this guy named Isaac Newton, pretty cool guy from what I heard, has derived 3 different laws of motion in order to analyze how forces will act on these bodies. And the first law states that if you have a body at rest or at a constant speed in a straight line, it's going to keep that constant velocity or stay at rest unless you have an opposing force act on it. And that seems pretty intuitive right off the rip. If I threw a baseball and someone was there to catch it on the other end, obviously there's an opposing force, which would be the guy catching it, to stop the motion of this ball. Vice versa, if you threw it and no one's there to catch it, it's just going to hit the ground and keep rolling. But then friction in the grass will slow it down, blah, blah, blah. But yeah, without getting too into detail on that, the next one is also a fairly simple one. It states that if you have a force exerted on a body, it will be equivalent to the body's mass times the body's acceleration. And we're going to explain that a little bit in this next part. The last law is that if you have an action, you're going to have an equal and opposite reaction. So if I pushed my hand against a wall, the wall is going to oppose it and create an opposing reaction. That wouldn't be the case if I blew my hand straight through the wall and destroyed it. That means the opposing reaction wasn't strong enough, and I'm not satisfying equilibrium in that case. That's a whole different topic as well. But now we can actually talk about units and relate that to why I even started talking about Newton's laws in the first place. So let's say we had an object, right? It's a mass of 10 kilograms, and the acceleration of gravity, if you don't know already, is 9.81 meters per second squared. And we know from that second law that force is equal to mass times acceleration. And if we use this formula, we can determine that the force created by this body or object is going to be 98.1 kilograms times meter per second squared, which is a super ugly unit that really just doesn't make sense logically. But if you think about it, this unit is actually equivalent to a Newton. See? It's related to the law, right? So 1 Newton, in simple words, just means the equivalent force required to give 1 kilogram of mass and acceleration of 1 meter per second squared. That's all it's equivalent to. And we're going to see, for a lot of these problems, we're going to have units that we've never worked with before. If you live in Canada, for example, you're going to have a lot of metric units. If you live in the States or elsewhere in the world, you'll have imperial. But that's going to be a common trope with all these problems, is that you're going to have to be comfortable with working with different units and just determining where to find the necessary conversions for some of these problems. Another important concept for units is that you can either have a super large value for a unit, or you can have a super small value of a unit, but it can be converted using prefixes to either bring them up to a more suitable demonstrated unit in your end. So let's say, for example, if I had 10,000 newtons, I can actually convert this using the prefix of kilo and just say I had 10 kilonewtons. And there's a lot of situations where this is going to be applicable in problems in the future and for conversion problems in general. But just for now, that's kind of the basics of what prefixes are for. Additionally, you have scientific or exponential form to demonstrate units as well. So you remember we just said we had 10 kilonewtons. If I wanted to display this in terms of newtons, I would simply do 10, and then for every 1,000 or 10 to the 3 newtons I have, that would be equivalent to 1 kilonewton. So I can actually write this as 10 times 10 to the 3 newtons. And that's pretty much the gist of scientific notation and prefixes, and we're going to see that obviously in problems, so don't you worry. The last important point is significant figures and rounding. This is a pretty important topic as well, which is going to be consistent as you go through different problems. In problems, you're going to be given values, right? And each number here, so for example, we have 431. These are 3 significant figures. The zeros before this aren't significant. The zeros after, if it was 431000, aren't really significant either. And since we're given 3 units to display, we can actually only show 3 units as a final answer based on what was given to us in the original problem. That's going to make more sense in future videos, but just for now, all you need to understand is that the number of significant digits are pretty much anything that is a non-zero value and not a 0 at the start or the end. The last important concept is rounding. It's pretty straightforward. If you have a number that's higher than 5, you're going to round up. If you have a number lower than 5, you're going to round down. But if you have a 5, it's going to be a little bit tricky because you may have to round up or down depending on what the leading or preceding number is. So if you had 1, 2, 3, 5, and you needed to round this up or down, you would have to make this decision based on the preceding number. And odd numbers are going to be rounded up. Even numbers are going to be rounded down. So if this was a 4, you would round down. If it was a 3, you would round up, etc., etc. And it's kind of a silly rule, but if you want to remember it somehow, down has 4 letters, even has 4 letters. It's kind of a way that I like to remember that. And if you're working with scientific notation, another trick that I like to use, so let's say you had 10,000. You can imagine you had a decimal here. You wanted to figure out what this would be in scientific notation. If you wanted to bring this decimal to here, it would have to move 4 spaces, 1, 2, 3, 4, meaning that this value would be 1 times 10 to the 4. It's a simple way to think of scientific notation as well. Alright, so now let's quickly solve these problems based on what we just talked about. We have 2 kilometers per hour, and it wants it in meters per second first. So for every kilometer, we have 1,000 meters. So if we want to cancel out the kilometer, we have to write it on the bottom based on where the kilometer unit is. That means on top, we will write 1,000 meters. Similar thing for hours. If we want to cancel out the hours, we write hours on top. And for every 1 hour, there's 3,600 seconds. And then solving that, we're left with 0.556 meters per second. And if we want this in feet, we have to cancel out the meter. So we bring meters to the bottom. For every 1 meter, we have 3.281 feet. Solving this, you're left with 1.82 feet per second. And the next question, that's your final answer, by the way, both of these. And the question 2 is asking us to represent the following quantity in correct SI form using the appropriate prefix. So we have 0.000431 kilograms. Pretty much this is just asking us what is the notation we should use if we wanted this in terms of grams. Well, this number, 0.000431, we have to multiply it by 10 to the power 3. So 10 to the power of 3 here is going to bring us to our gram value, meaning that our final answer will be 0.431 grams. And we still have 3 significant digits based on what is given in the original problem. So that's pretty much the introduction to units and dimensions for mechanics. But in the next video, we're going to do a couple more problems that are a little bit trickier.